Hello once again, class, and welcome to another mock lecture. In today's video, we're going to be talking about the derivatives of trig functions, beginning with the derivative of the sine of x. Now, if we take what we know about sketching derivatives from a graph, we could see that sketching the graph of the derivative of sine of x should look relatively familiar. Here's a graph. The dotted line represents what the derivative of sine of x would look like. Things to notice are that the derivative has zeros when sine of x is either 1 or negative 1, really where its slope is 0, which happens at negative pi over 2, pi over 2, 3 pi over 2. It'll happen again at 5 pi over 2, negative 3 pi over 2. It happens as well. It's above the x-axis whenever the sine of x is increasing, so it's positive between negative pi over 2 and pi over 2. And at this point, it should not be a surprise that, in fact, the graph that we're talking about, the graph of this dotted line, is indeed the cosine of x. Cosine of x actually models the slope of sine of x, which is pretty cool. But let's actually prove it, mostly. So we're going to let f of x be equal to the sine of x, and we want to find f prime, so that means I'm using the limit definition of a derivative. The limit as h approaches 0 of the sine of x plus h minus the sine of x divided by h is where we're going to begin this whole endeavor. Now, this proof starts by using a sum identity for the sine function, namely that the sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta, and that's where I'm getting this thing from. This thing just comes directly from this via a trigonometric identity, and if you want to search the sum angle identity for sine on Google or something, it's going to tell you this. It'll probably be in terms of alpha and beta instead, though. That's all I did for the first step. For the second step, I went ahead and I associated some stuff. I kept these things together and made them their own fraction, and then I took this piece and made it its own fraction. The denominator has to go to both pieces, though, because that's the definition of breaking apart fractions like this into separate sums. And the reason I broke them up this way is so that from this one I could factor out a sine of x, and from this one I could pull out, not really factor here, but pull out, separate, maybe is the right word, a cosine of x for this thing, which allows me to use a bunch of limit laws. What are we using here? We're using the product law, we're using the sum law. That's actually it. Those are the only two limit laws we're using, a product and a sum law. Product law in two different cases, sum law in one case. And at this point, we reach a bit of a roadblock. I think these things are relatively fine for just direct substitution, but it's these things that we have to kind of worry about. What is the limit as h approaches 0 of the cosine of h minus 1 over h? And what is the limit as h approaches 0 of the sine of h over h? And this is where we're going to kind of cheat a little bit. You can prove both of these limits actually with the squeeze theorem, but there's a lot of setup involved in it. And honestly, you could Google the proofs of these things. I just wanted to mainly prove the derivative of sine of x in this video and not super focus on these specific limits. But we do need them to actually prove what the derivative of sine of x is. So I'm going to show you evidence for why we know what these limits are, but I'm not explicitly going to prove them for you. The first one, the limit as h approaches 0 of the sine of h over h, actually, if you've been following my series, should look familiar because we talked about this in the very first calc video I did. Let's roll the clip. So again, as we're approaching 0, as x approaches 0 from the right-hand side of the graph, we again see that our values, our y values, seem to be approaching 1, and so my guess is going to be that the limit as x approaches 0 of the sine of x over x is 1. Okay, so we get that it's 1. I also included some graphical evidence, right, when h is approaching 0, I guess really we're kind of graphing this so it's like it's an x, but whatever, the variables are interchangeable. Just pretend this is the h-axis that we're looking at here. As h approaches 0, it's pretty apparent that the limit exists, and in fact, the limit is equal to 1. The other one, the limit as h approaches 0 of the cosine of h minus 1 over h, I'm just going to give us graphical evidence for being 0, which is what it is here in this case. It appears that the limit exists, and in fact, it appears that that limit is 0. The left and the right-hand side of this graph agree. So, okay, we know the limits of these two things now, or at least we have strong evidence for them being 0 and 1 respectively, and so I'm going to do that. I'm going to do that substitution. That's 0 here. This one's 0 right there. This one's 1. Okay? by these two limits that we haven't proved but have strong evidence for. At this point, we can go ahead and use some direct substitution, and we just get the cosine of x. Now, I skipped some stuff there, so let's go over that. The 0 times anything is just 0, and then 1 times the limit as h approaches 0 of the cosine of x is just the limit as h approaches 0 of the cosine of x, which you'll notice has no h in it at all, and so h approaching 0 doesn't affect what the cosine of x is, so it's just the cosine of x, and that's by, we're going to say, quote-unquote direct substitution, even though there was really nothing to substitute. We didn't plug 0 in for any h's since there are none. All right, so the derivative of sine of x has been mostly proven, shown, let's say shown, has been mostly shown to be the cosine of x. Phew, bit of work. We got 5 more to go. All right, so cosine starts off much the same as the sine of x. We're going to let f prime be equal to the limit as h approaches. I'm just kidding, you guys. I'm not going to make you sit here and watch all these proofs. We're just going to take these at face value. And actually, once you get these two, all the other ones kind of fall into place with the quotient or product rule. For example, the tangent, once you're given the derivative of sine of x is cosine of x, and that the derivative of cosine of x is negative sine of x, tangent is just sine of x over cosine of x, and you can just use the quotient rule on that to get the secant squared x function as the derivative of tangent x. But if we go through them, the derivative of the cosecant function is negative cosecant x times cotangent of x. The derivative of the secant function is one of my favorites. It's secant x tangent x. And then you got the derivative of the cotangent of x, which is equal to negative cosecant squared x. Now, honestly, I could stop the video here. Here's the whole point of it, to just show you what the derivatives of the trig functions are. But that wouldn't really be a mock lecture without any examples. So let's just do a couple. All right, example number 1. Differentiate the quotient x squared divided by secant x. Now, I did say quotient, and that might prompt you to think, oh, well, we should use the quotient rule to do this thing. You can, but now we're working with trig functions. And whenever you're working with trig functions, there is a bunch of cool stuff you could do to get around almost everything you'd like to avoid. For example, while you could use a quotient rule in this one, you'd get this, right? The derivative of the top function times the bottom function minus the derivative of the bottom function times the top function, all divided by the square root of the bottom function. That is something you can do. Instead, though, you can bring secant x up into the numerator as the cosine of x function. X squared times 1 over secant x is the same as x squared times the cosine of x, and then you can just use the product rule on that thing. And that's what this is. This is product rule stuff. Derivative of first function times second function plus derivative of second function times first function, and that's way easier to differentiate. The derivative of x squared just gives you 2x here, so this derivative is this, so it's 2x times cosine of x. The derivative of cosine x we now know is negative sine of x, and although we didn't prove it, we could, much the same way that we proved the derivative of sine of x, times x squared. So we just get this, and you're basically done. I just reorganized some stuff a little bit. I moved the x squared in front of the sine x. I made the plus minus just a minus, and we're done. This is the function that models the slope of this one. Well, really, this one. X squared over secant x. Example number 2. Find the x values for which this f of x function, defined to be the secant of x divided by 1 plus tangent of x, has horizontal tangent lines. So we got to keep in mind, what does that mean? What is a horizontal tangent line? Well, that's when your slope is 0. Okay, so in this particular example, I decided to get everything in terms of cosine of x and sine of x. Again, we could just straight up use quotient rule on this, but I love trigonometry, and if I can change something into something that to me looks easier to use, I'm gonna do it. So what I did is I was like, well, you know what? I don't want things in terms of secant and tangent. I'd like to get things in terms of sine and cosine. So I actually multiplied, and although I didn't explicitly write it out for some reason, I multiplied the top and bottom of this expression by the cosine of x. So I'm multiplying by 1. I'm not changing the integrity of this fraction at all, but I just multiplied straight across, which means I had to distribute this cosine here, and that's fine. But the cool thing is, when you multiply secant with cosine of x, you just get 1. They're reciprocals. Secant is 1 over cosine, and when you multiply 1 over cosine with cosine, they cancel, you just get 1 in the numerator. Okay, that's cool. In the denominator, when you distribute cosine of x to the 1, you get cosine of x. But cosine of x times tangent of x is just sine of x. Tangent of x defined to be sine of x over cosine of x, and when you multiply by cosine of x, the cosines cancel, so we just get sine in that last position. So this is what I'm going to differentiate instead of this, and I'm going to get the same answer. So the derivative of the top, which is 1, times the bottom, which is cosine of x plus sine of x, minus the derivative of the bottom, which is cosine of x plus sine x, times just the top, which is 1, divided by the denominator squared, cosine x plus sine x, quantity squared. That's the quotient rule. The derivative of 1 is 0, so that's just gone. This whole thing is just gone because it's 0 times anything, that's 0. The derivative of this inside piece, cosine of x plus the sine of x, can just be you can just use normal differentiation rules there. The sum rule is what I'm using. So the derivative of cosine of x is negative sine x. The derivative of sine x is cosine of x. And then to get to this last piece, I just distributed the negative sign, and then this became positives and this became negative. So here's my derivative. Now, when you're trying to figure out where something has horizontal tangent lines, you just need to figure out when is your derivative 0, because that's when you're going to have a slope of 0. That's what creates a horizontal tangent. But you'll notice that this is kind of like a rational-ish looking function. Rational functions kind of are explicitly defined to be, you got a numerator and a denominator, they're both polynomials. We definitely don't have polynomials here, but it's set up in a ratio, right? It's a fractional type of function. And the only way to make a fraction 0 is if the numerator is 0. You could almost think about it as I'm multiplying both sides by cosine of x plus sine of x quantity squared to get rid of it from the denominator, but you're multiplying it on this side by 0, and so that's still 0. And on the left-hand side, it just cancels. So we just need to figure out when the sine of x minus the cosine of x is equal to 0, or maybe even better, when is the sine of x equal to cosine of x? That happens in 2 places on the unit circle. One of them's in quadrant 1, where both of them are positive, and the other one's in quadrant 3, where both of them are negative. And of course, I'm talking about pi over 4 and 5 pi over 4, right? That's what this angle and this angle is. Both of which, by the way, are separated by a measure of pi. In fact, if I take pi over 4 and I add pi to it, that gets me to 5 pi over 4. And that's why I'm saying, well, look, whenever this function has horizontal tangent lines, which is when the sine of x, as we discovered, when the sine of x is equal to the cosine of x, that is going to happen at pi over 4 plus any pi times an integer. Multiply by 10. So you'd have 41 pi over 4, right? There's going to be a horizontal tangent line for secant x over 1 plus the tangent of x there. Because at 41 pi over 4, that's when the sine of x is equal to the cosine of x. That's one of the solutions. So the way that I wrote my answer was that f has a horizontal tangent anytime x is in one of these forms. So I said pi over 4 plus pi n, where n is some integer. So n could be 0, in which case pi over 4, there's a horizontal tangent. N could be 1, in which case you'd get 5 pi over 4, and that's the one that's within the unit circle. But then anything that's coterminal with those two angles is going to show up from this expression as well, and so that's where f has horizontal tangents. Now, you might be a little bit skeptical in this whole, like maybe you're not jiving with it. I don't want to find things in terms of sine and cosine. I don't want to simplify this. I just want to use the quotient rule on this thing and solve. Well, you're going to get the same thing. And rather than me kind of going through and explaining all of it, I'm just going to unveil these slides one at a time so that you could pause the video at any point and see that I'm still abiding by the rules of trigonometry. I did have to use an identity at some point, specifically here, where the tangent squared of x minus the secant squared of x is just equal to 1. But I eventually get to something that's more manageable, right? And then I can figure out when the numerator of that is equal to 0, which actually only happens when the tangent of x minus 1 is equal to 0, because the secant function is never 0. So we don't have to worry about that. You only have to figure out when the tangent of x minus 1 is equal to 0, which is when the tangent of x is equal to 1, which still happens at the pi over 4 angle and the 5 pi over 4 angle. So I used, again, pi over 4 plus pi n, where n is some integer. All right, and that's it. I could do a ton more examples that involve secant and cosecant and all that stuff, but I just wanted to give us a rundown of what the trig derivatives are, We used a couple of them, namely sine and cosine here. Anyway, hope you guys learned something. If you have any questions, please leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.